Hi, I'm Cheryl Leach. In this problem, we're going to be approximating the area under the curve 1 divided by the quantity x squared plus 1 squared on the interval from -1 to 3 using 4 rectangles. We're going to be using the midpoint rule to do this. Now typically, when I would start a problem like this, I would begin with the graph of my function so that I could get a visual representation of what those rectangles really look like compared to the area under my curve. However, if you take a look at that function f, it's fairly complicated. Now, we have the techniques that will allow me to graph this from calculus. However, those techniques are usually complicated and time-consuming. And to be honest, in a problem like this, I don't need that level of accuracy for my graph. So I'm going to go ahead and just start trying the midpoint rule. Now, that being said, it's always a good idea to have a visual idea of what's happening. So instead of looking at the entire graph, I'm going to be looking at that representative element that we'll be using in our midpoint rule. That is a rectangle. So if I draw in a rectangle, I know that I want to find the area of this rectangle. And these areas of the rectangles are going to be what I use to approximate the area under my curve. Well, what do you need to find the area of a rectangle? Well, the first thing you need is the width of the rectangle. How wide across is it? Well, I know that my entire interval goes from -1 to 3, and that I want to use 4 rectangles to do this. So I can calculate the width by using delta x, which is b minus a over n. And in this case, I'll have 3 minus a -1 all over 4. This is going to be 4 over 4, which is 1. So each rectangle will have width 1. Well, what's the other piece of the puzzle that I need to calculate the area of a rectangle? Well, it's the height of that rectangle. Well, I can choose a height in a variety of ways, but in this case, I'm using the midpoint rule. So what we want to do is we want to look at our rectangle and find the midpoint, and then use that value, plug it into my function value, and say that is going to be the height that I'm going to use for my rectangle. All right, so let's go ahead and take a look at the various intervals that I'll be using. I'm starting at -1, and I know my first rectangle has length 1, so that will take me to the point 0. So my first interval that I'll be using is from -1 to 0. What's the midpoint of that interval? Well, if you add these two numbers together and divide by 2, you get -1/2, which is the midpoint. Well, that only tells me the location of the midpoint. It doesn't tell me the height of the rectangle. In order to calculate the height of the rectangle, you want to plug that value into your function. So you want to know what f of -1/2 is. All right, well, we can do that by plugging into my function. So I'm going to have 1 divided by 1/4 plus 1. So that's going to give me 5/4 squared, or 25/16. And 1 over 25/16 is 16 over 25. In a similar way, we'll look at the next interval. I'm going from 0 to 1. And the midpoint of that interval is going to be 1/2. Plugging 1/2 into my function, because that will calculate the height, I'm going to have 1/4 plus 1, that's 5/4 squared, and then 1 over that value is again 16 over 25. The next interval will be the interval from 1 to 2. Adding these together, I have 3 divided by 2 for the midpoint, or 3/2. Calculating the function value, I have f of 3/2, and that's going to be 16 all over 169. My last interval will be the interval from 2 to 3. Adding those together, I get 5 divided by 2 is going to give me a midpoint of 5/2, and f of 5/2 equals 16 all over 841. Now I have all the pieces that I need for this puzzle. So let's go ahead and find the area of my region. The area of my region is approximately equal to the area of all of these rectangles summed up. So my first rectangle is going to be, well, let's mark this down. The first rectangle plus the second rectangle, and so on, till I have all 4 rectangles. The first rectangle is the width times the height. The width in this case is 1. The height is f of -1/2. On to my second rectangle. The width again is 1. The height this time is f of 1/2. For the third rectangle, again, I have a width of 1. This time, I have a height of f of 3/2. And for the last rectangle, a width of 1 and a height of f of 5/2. Now, I notice that all these coefficients are 1. So really, all I have is f of -1/2 plus f of 1/2 plus f of 3/2 plus f of 5/2. With some number crunching, I will get 16 all over 25 plus 16 over 25 plus 16 all over 169 plus 16 all over 841. Now at this point, you might want to pull out your calculator to do a little number crunching. And if you add these fractions together, so we'll have 16 divided by 25 plus 16 divided by 25 plus 16 divided by 169 plus 16 divided by 841, and we get approximately 1.394. And I have rounded this. So this is approximately the area under my curve. Well, let's go back and see how this relates to my picture. Well, I know when I started this process that I wanted to look at the first rectangle and it would have a width of 1. And I know that I'm going to use the midpoint to calculate the height of that first rectangle. And that midpoint happened at -1/2. So let's see, how tall should that be? Well, it should be 16 divided by 25. Well, just to get a rough idea, 16 divided by 25 is about 0.64. So let's put that right about here. And that's going to represent the height of that first rectangle. So let me draw that in. For my second interval, my midpoint was at 1/2, which is right here. And the height of my rectangle is 16/25. It's the same height as before. For my third rectangle, the midpoint is happening at 3/2, and the function value is 16 divided by 169. So let's see, 16 divided by 169 is 0.09. So that's quite small. So let's say that's right about here. And my rectangle is going to look like that. And finally, for my last rectangle, the midpoint is happening at 5/2. The height is going to be 16 divided by 841, a very small number. That's 0.02. So you can barely even see the height there, but it's a very, very short rectangle. Okay, now, how does this help me visualize my area? Well, remember that the whole point of finding that height at the midpoint was so that this point lies on the curve. Remember, that's the value of the function at the midpoint, so it'll be a solution point to my function, which tells me that this point, this point, this point, and that point are all solution points to my function. Now, I'm still having a little trouble figuring out what the graph looks like. Well, one other thing that could help is checking out the midpoints, or not the midpoints, but the endpoints, excuse me. So, at -1, what happens to my function? Well, at -1, I'm going to have 1 plus 1, which is 2, squared, so that'll be 1/4. So, this point is also on the graph, -1, 1/4. And how about the other endpoint at 3? 3 squared is 9, plus 1 is 10. 10 squared is 100. That's 1/100. That's a very small number. That's the smallest one we have yet. But it's still above the x-axis. All right, well, I'm feeling a little better about this side of the graph. I see several points that I could connect together to get a visual of the graph. And when I move over on the other side of the y-axis, I see a couple of points I could connect together as well. But I'm not really sure what happens between this solution point and this solution point. Somehow I must turn over. Well, I noticed that the y-intercept is right in that location where I'm a little fuzzy on what's going on. So let's go ahead and figure out what the y-intercept is. You calculate the y-intercept by setting x equal to 0. And if x equals 0 in my function, I'm going to have 1/1, which means 1 is the y-intercept. So that connected a few dots for me. So let's see, if I draw a curve that goes through all of those points, I'm going to have something that looks like that. Now, this is not as accurate as you would get if you used all of your calculus techniques, but can you see that the area under the red curve can be approximated by the area of these rectangles? I hope that helps. Thanks.